We'll get a start on. So welcome to the Australia-Israel seminar series. Um, I'd like that we first acknowledge the Jagera people and the Turrbal people. They are the traditional custodians of the land on which we gather here today on my side here in Southeast Queensland. We pay respects to their elders past and present. We extend that respect to Aboriginal and Torres Strait Islander peoples here today and to Indigenous peoples throughout. And today it's a great pleasure to have Dr. Helena Vitoshkin from Volcani Institute present. And she'll be speaking about crop modeling of spectrum splitting agrivoltaics in Israel. So very much looking forward to your talk. Thank you, Helena. It's all yours.
Hi, hello everyone. Thank you for introduction. My talk today about agrivoltaic crop modeling. I suppose people know, but if somebody doesn't know, that agrivoltaics is this idea to build the photovoltaic panels on the agricultural fields and combine the production of electricity and growing crops. And then this study, based on our previous study done on the modeling of electrical performance and crop performance under spectral splitting collectors that I will introduce later. Okay, a few words about Volcani Institute. The institute was founded in 1921. We have already celebrated our 100th anniversary. So you ask about researchers, so I have this information on my slide. We have 200 researcher scientists and 25 graduate students. Our central campus, located in Ministry of Agricultural buildings, and comprises 6 separate institutes: agricultural engineer, soil, water, plant protection, animal science, post-harvest, and plant sciences. We have also 2 off-campus research stations, one in the Gilad in the south of Israel, studying on semi-arid agricultural topics, and another in the north in Neve Yair, focusing on sustainable methods. So Israel have a large resource of solar coming from the sky. You can see in this solar resource map. Besides this large solar resource, Israel's different climate regions, such as Mediterranean and the desert and mountain, provide the ideal setting for agri-PV study. It has become a kind of research lab from which many countries in the world can profit. So our study, empowered by Israeli startup capability, is building bridges between agrotechnology from New Zealand to Europe, from Europe to and the United States to Africa and Asia. So, is it now a question? Is it feasible to install the photovoltaic panels in agricultural fields in Israel? So in Israel, we have 4,000 square meters of land is currently used for agriculture, but more of this land is designated for future urbanization. So we have approximately 1,300 kilometers square. Regarding crop distribution, most of orchards growing in the north and field crops are growing in the south. Now the question is, which of the existing crops are suitable for agri-PV? The first parameter is the growing space. According to the data provided by the Ministry of Agricultural Digital Information Technology Division, GIS Division, Wheat and other open field crops are grown approximately on 40% of all land. Olives, potatoes, and avocados are grown another 15%, and other crops take about 18%. The various other crops that occupy less than 1% of the available land have no effect on results. They are excluded from the analysis. So, recent publication said that projected national electricity production is 72 gigawatt for 2050. It will be available to the agricultural areas that I showed you before. On the other hand, the same study indicates that 37% of crops will lose yield due to shading from the PV installation. 2% of crops will not suffer from the shade, showing a neutral response, and 11% will benefit. Notable, there is no comparative data that 50% of crops overall, but if we apply proportionally the data we do have to this unknown 50%, we can predict that estimated 70% of crops could lose their yield with standard PV installation. So our calculation shows that the economical benefits from land use from PV use only is 10 times higher than possible from agriculture. This unfortunately provides a clear temptation for farmers not to spend time and money to grow in crops. So the question then that have been asked are, where should PV panels be installed to minimize damage to plants? How we can balance between yield and electricity production? And additionally, how should be regulated all these systems to avoid PV-only land use and to keep the agricultural on the market or in the picture. So to address all these questions, the Israel government has released a call for agri-PV pilots, approving 35 groups to install different technologies across different crops. So, for shade-tolerant plants, standard panels is a good solution. But for shade-sensitive crops, which are growing on much larger fields that I showed in the previous slide, for this crop, special treatment is required. One of the possible solutions is a spectral splitting approach, offering an idea to split sunlight spectrum between plants and PV modules. PAR, or photosynthetic active radiation, or part of PAR, for example, red and blue spectra, can be transferred to plants, and near infrared wavelengths responsible for heating and evapotranspiration can be redirected to PV modules. This approach is not a new idea. There are several researches and commercial technology already on the market. But to understand which crop can be growing under such system with modified sunlight, we have do extensive crop modeling study. So we tested several commercial codes, aquacrop or upstream or workforce, and we found that it is complicated to change the code in order to produce modified sunlight. And finally, we choose DSAT, which is well-established model with many calibrated plant varieties, and we were able to separate PAR and other spectrum within this code. So we modified it, and after modification, we have to validate. So to validate the results of spectrum splitting modification of DSAT code, the outdoor growth tests of different plants were carried out in experimental site here in Volcani Institute. Plants were grown under filtered light, and final results were compared with those predicted by model. Both simulation and experiment show the positive trend in terms of leaf area and dry weight, which were good enough to continue modeling. So the impact of filtered light on yield have been investigated across diverse Israeli climates and diverse crops. 4 cases were compared in terms of annual average radiation. The open field is used as the values which have all radiation, 1. Standard agrivoltaics within 20% rule, which is a regulation limit which can be allowed to produce 20% less crop in agrivoltaic site. If it will be more loss, so the system will not give the permits and licenses. The third case is a spectral splitting, owing the idea that I showed previously. And the third one, the last one is a dense spectral splitting. So we can, if we can transmit more parallel to the plant, so we can install the panels in much closer each and other, and in such way we can produce more energy. So we use 10 different climate locations covering 92% of agricultural lands, and we use 10 common crops according to the gross land occupied by this crop in Israel. So this here is the main yield results. On the x-axis you see different plants, and the y-axis is a yield as a function, as a percent of open field. So 100% is the open field crops without any losses. 80% is the regulation limit that I mentioned before, that allowing for such kind of agrivoltaic system. So the result shows that spectral splitting case can produce a much yield than the standard agrivoltaics system, and standard agrivoltaic system hurts most of plants, if you can see, it's relative to 100%, and such crops like wheat and potatoes even are lower than regulation limit. But in the spectral splitting case, all crops are within this level. So just what is happening? Okay, here. So if we use a dense spectral splitting system, so we can produce even larger amount of crops relative to open fields for shade tolerant crops like cabbage, tomato, and other crops will not suffer from the yield loss, and crops that are shade sensitive shows a similar behavior like spectral splitting. In terms of irrigation, all systems led to lower water demand for crops, with dense spectral splitting has high effect. That means that farmers can save water and reduce their water cost. This graph shows the average annual electricity generation for 3 agrivoltaic systems over the climatic groups. You can see that dense spectral splitting produced almost the same amount of electricity as a standard system, and the spectral splitter, on the other hand, generate about 2/3. This graph shows the average annual electricity generation for the three agrivoltaic system over the all climatic groups that we'll examine. You can see the dense, something wrong? Okay. Annual electricity generation was produced in 22. It is blue line, and expected in 2050. It's a red line. By employing the system on the land with crop tolerant shade with no yield losses, we can produce 10 terawatt per hour in spectral split and only one in standard agrivoltaic system. By allowing 10% of yield loss, we can produce 67%, much more. And by allowing 20% of load, which is a regulation limit, we can generate 109 terawatt hour. It is considered amount, and we will approach to this 2050 expectation, annual electricity demand expectation. So if we use all fields that we examine, so we will again have the similar electricity production, but then spectral split and in standard agrivoltaic. But in case of standard agrivoltaic, we have a huge loss in crop yields. So in conclusion, as we see, the spectral system worked better for almost all crops we studied. We can use 22% of available electricity without yield loss. We also well in the 20% of loss rule. We show that denser installation of panels can produce the same energy as in standard agrivoltaics, but with a little to no negative impact and less water consumption. And the last slide, I would like to show you short clips that show one of the first pilots in Israel already been initialized in Kibbutz Revadim by Doral company. This pilot contains 8 different treatments over avocado orchard, testing the best combined practices to combine electricity production and crop growth. And I think I can take a few questions until you can show the movie.
Well, first, let me clap in the name of the rest of the audience and those watching later. Thank you very much, Helena. Yeah, are there any questions or thoughts? I have some as well.
I did have a few questions. So
Go ahead.
would it depend on the crop itself? So different crops, would they require different wavelengths of light in order to grow? So you can tailor the splitting itself to the crop and then in the stage of growth, so that you can maximize the crop yield as well as the electricity generated?
No, this is actually the main question of agrivoltaic fields. Nobody knows how the plant will reflect dynamic shading and or modified light shading. Most of people study indoor LED lighting, growing crops under indoor control environment with LED lighting, but it's completely different topics because LED lights have a different spectrum. A spectrum is different than the sunlight. So there is a still open question how to manage the light quality and light intensity in order to Now we're not talking about improve crops, we're talking about to minimize the damage.
Mm.
But potentially, sure, we're all looking for solutions which will improve crops.
Okay, תודה.
Thank you. Are there other thoughts or questions?
Helena, thank you for the great talk. What is the farmer's response to having the solar panels on top of their crops? Do they like it? Do they see the benefits? Or do they see it as a necessary thing? Yeah.
Yeah, before 7 years, just started to think about this idea. I have a lot of criticism about this, but now situation is like 50-50. 50% very much. 50% of farmers want are interested very much to install the panels in the fields. It is because they produce electricity much worse economically. As I said, you can have 10 times profit higher profit than if you produce the crops and without any problems. Just put the panels. They don't need any treatment or minimal treatment. And this is the main problem of the Ministry of Agriculture. And other more other farmer are afraid of this idea and they think it will crush the agriculture. They have different opinions about this. Not just the farmers, also other social communities show the criticism. So we're interesting to see green landschaft, green sites, and instead of this, I bring my panels, and they don't want to see this. Therefore, my idea is to show how to use this system in optimal way. And similarly, as Minister of Agriculture, I'm put my efforts to minimize the damage. Because I know this idea will come in, and it's not just a question of farmer interested or not, because we need solar energy and we need secure energy, and we can allow ourselves just to put several power plants in the certain locations of the country. Or we need to build micro networks and to bring the electricity close to the city, and a city already occupied with agricultural fields, so we don't have another choice, just to combine these systems. And my mission is I think we need to do it in a smart way.
That's really interesting. And I guess you always have early adopters that you can work with and then show the proof of concept and expand from there. But yes, you certainly have particular restrictions on land area, on
Yeah.
that energy security and and also, you know, the community acceptance. And I think Australia's dealing with similar challenges around solar energy at this point as we expand our renewable energy system. So it's really, I think, yeah, Israel's obviously exploring really fascinating options. So thank you.
Yeah. Yeah.
Yeah, thank you. I'll ask a quick final thing, if you don't mind. So I must say, I do a bit of consulting for an Australian startup that actually looks at solar farm maintenance. So it's a big problem to do solar farm maintenance, of course, to clean the panels, etc. And here I see synergies because your agricultural workers already have to be on the ground. So you have an ability to actually have panels that can be very maintained. So, right, in the sense where in a solar farm that's not with agriculture, it's extra cost to send workers over. So my
Sure.
question is, have you looked at kind of these types of benefits of synergies from, having the workers there and they could potentially do some form of manual labor
Sure.
needed for panels and also vice versa sensors. So you've got the solar panels, so you can also have kind of smart agriculture sensors because you've got the electronic machinery, well, electrical machinery, I should say. That's my
Yeah,
first
this
question.
is our dream, and these advantages are clear. Once you have electricity and construction in the field, you already have actually controlled environment, and you can protect crops from external extreme weather. And also,
Mhm.
as your question regarding to panels, and panels have much a longer list of advantages because in the crops, because they have a lower temperature crops. If you compare the solar farm in the desert area and in the agrivoltaic field, so in the desert area you have a very high heat. Radiation is reflected from the ground, and here the panels can be cooled by trees because the trees are evapotranspiration, so it's very comfortable temperature for the panel and can produce more energy. And another thing, in agricultural field, the no, it's less dirt, so there are no sand which is coming with the wind. We show the almost minimal cleaning services were requirement in agricultural fields because the environment is it's clean, more clean than if you put it in the desert.
Yeah.
Uh, one problem is higher construction. This is an investment. The construction can be 4 or 5 meters higher, but other maintenance investment are lower because you have workers in the field, so it is combined in one system, and you can clean the panel and use this water for irrigation, for example. So all this idea of building panels under the fields, it's come from electricity production companies. They're interested to build such a system.
Gotcha.
And
Yeah.
as also you said, the main problem here is the logistic cost and maintenance and cost if you build it far away from the residential area, right? And this is a main purpose, like why this idea came up.
Mhm.
To minimize the logistics costs. But I think if you know, we have a plant, solar plant in Stebokel. If you probably you hear, but
Oh, yes, yes. Mhm.
if you visit country in the south, in the direction of Dead Sea, you will see the
Yeah, the high one. Yeah.
high one,
Yep.
and it is the this plant is actually stuck because of logistic costs. We can
Oh, yeah.
produce enough energy, but cannot to bring it to the customer.
Yeah. Oh, very interesting. Well, on thanks a lot. So on that note, Helena Vitoshkin, would really like to thank you, and all our joiners or those watching on YouTube can also search you up, and I'm sure you'd be happy to collaborate and communicate further. Um,
Yeah,
yeah, really appreciate your time for taking the time you've taken to present your work, and we hope to keep in touch and do much more.
yeah. I also very hope that we will have some collaboration and visitors, and they're always welcome in Vulcan Center.
Wonderful.
Okay,
Okay, have a good day in Israel and good afternoon in Australia. Bye bye.
okay,
Bye. Thank you.
bye.